Okay, welcome back. So this is the second part of our discussion about statistics and forensic science. I've called this section exploring data. And so partly what we're going to do is run you through some basics about working with populations and samples from populations, and then talk about how to describe the data that you've collected. And so without further ado, let's go. All right, so I already kind of introduced this as an overview, but so some of the topics would be populations and samples, data types, variables and parameters. And so variables belong to samples, and parameters are characteristics of populations, and we use variables to estimate parameters. One thing that you do when you've collected data is you need to sort of describe it. And so two characteristics of that description are: what does the middle look like? What does the average look like? As well as what's the variability? Are all individuals alike, or are there differences? And so description about the middle, description about the variability about the middle. All right. So let's demonstrate a convenient sample. Well, convenient, what would be convenient? Well, I could take an individual from every row. Since I'm going to say I want to take a sample size of 5, then I'll say, well, if not one from every row, something close to that, right? So here's an example. I set up my convenience sample of 48 individuals, and then here's the code for drawing out 1 every 10. All right, and so this was the sequence I got. And so I go and I draw my population. If the goal of sampling is to get a representative sample, this isn't too bad. 5 out of 48, so roughly 10%. Okay, and I got 20%, 40% black, and I got 20%. Right, 1 out of 5, 1 out of 5, 1 out of 5, 2 out of 5. All right, so pretty close. We started off with 60%, so we're a little underrepresented, but I got 1 from each group, so it looks pretty good, right? So let's go ahead and try random sampling. And remember, random sampling is statistically a preferred approach to doing this. So anyway, here's my sampling design. So my population size 48. I'm going to draw 5, replace is false again. So let's take a look. 1 sample. All right, so what is that? 80% black, 20% blue, and then 0% green, 0% red. So this is not necessarily a representative sample, right? Okay, so here's another random draw. This is 100% black. And my last one, okay, so that one's, so that's what, 40% again. Okay, off we go, all right? So the point about it is every time I do a sampling and it's random, by chance alone, I'm going to get a different looking sample. So this will be important later on when we talk about asking questions about data, the inference, since you're working with samples. Each sample is more or less representative, and so your conclusions depend on how good your sample represents the original population. And there are limitations to this. And the limitations, sampling can always miss some individuals, right? Okay, so kind of if you were just following along there, you should have noticed that the convenience sample did a kind of a better job than the random sample, right? I missed the red, but that was a convenient sample. So how can you, well, here's the point. All right, so you have subpopulations, and so you're going to probably have to modify your random approach. You can't treat it all as one population. You would have to try to sample by proportions in order to get a representative population. So something between a convenient sample and a random, truly random sample is what you're going to have to do. The point about it being is that with sampling, minority groups will tend to be missed, and also the majority groups might be underrepresented relative to their proportions if you do random sampling alone. Okay, so 2 different approaches to sampling. Got to be careful about the conclusions that you make, and think about how to recruit individuals into your sample for study. The first order of business is certainly for continuous data, you would want to describe what's the middle like, what's the most common observation. And so you've already been introduced to the arithmetic mean. It's just simply you add up all the observations and divide by the sample size. Okay? You may see a table where the observations occur as counts. So we had for the an observation of 4, we saw it 4 times in our sample. For 5, we saw it once. For 6, and so on, right? So you might use what's called a weighted mean, which is 4 divided by the total here gives you the frequency, right? So what do we got here? We got 8, 11, 13, 18. So 4 divided by 18 is what? 22%. Okay, so on and so forth. And so that would be what we would use here, 0.22 times 4 divided by 0.22, and that would give us an individual weighting for that one, and we'll repeat that algorithm for each one of these, and what you would find, of course, is that the two values will equal the same thing. Okay? In R, this is how you would do the coding. You would just enter your variable, put the elements in there, and then you just simply go mean x, and off it goes. The weighted mean, I'll give my list of my observations, and then I give my weights. Oh, it's 15, not 18. I can't add. Okay? And then, of course, the means are going to be the same. Okay? So let's talk about estimates. All estimates come with uncertainty. Statisticians call it error. It's not error of the kinds of we made typos. It's not error of the kinds of we misplaced our spreadsheet cells or something like that. It's because we sampled from populations. And if you recall, when I was doing simulations there, sampling from the populations, each one of my samples got slightly different diversity, right? Some were more of one type and less of another. Okay, and so that's what we mean by error, is that you only sample once, and so you have to account for the fact that your sample may lack representation. Okay, so we can, because of the 100+ years of people doing these things, we can go ahead and figure out what that error is likely to be based on our samples. And so we calculate things called confidence intervals. And so an approximate confidence interval, and it's kind of missing here, is plus or minus 2 times the standard error of the mean. Just an approximate, but it's a good, if you have large samples, it's a pretty good approximation. Okay, and we'll introduce you to the standard error of the mean here in just a moment. There are other means that you may run into, in particular the harmonic mean is when you have ratios or frequencies or rates, and so it has a slightly different formulation, and all of them they can't be less than 0, so that's something. And another one we use when doing gene expression analysis quite a bit is the geometric mean. So again, different formula from our simple arithmetic mean, but you use it when you have different variables, like different genes, and the scales can be quite different. So some genes are expressed a lot, some genes expressed just a little. Okay, so at, already at the very beginning of statistics, we're introducing you to ideas that you probably aren't familiar with. You more than likely didn't know that there was multiple ways of conceiving what's the middle, and it depends on the data type, which formula you use. All right, so this is code for how to figure out how to get geometric mean and a harmonic mean in R. I'd also point out getting the estimate, getting the answer is all you need. So if you just refuse to use R, that's fine. So here's the simple function calls that you would use to get geometric mean or harmonic mean in Excel or other Excel-like spreadsheets. So that's a pretty simple measure. So I just described relating these measures. If your data are more or less symmetrical about the middle, then the median, the mean, and the mode will all be the same number. But if you have a skewed distribution, so this is an example of like the salary, all right, a few individuals have a very large salary, okay, so very few, so that the mean gets dragged out to the right there. So the median would be a better estimate of the middle of that distribution. Okay, all right, so we've described the middle. That's one part of describing your data set. What does the average one look like? So you can appreciate that without some description of the variability, you're sort of not seeing the whole picture. So these are a couple of simulations here where the mean is the same between the left graph and the right graph, but I drew from a much more variable population on the left compared to everybody was pretty much the same on the right. And so clearly those two data sets are different. They're different in their variability. So we want a way to quantify that. So the statistics of variability are basically the variance. And so if you have the whole population, okay, then you would calculate the population mean, and for each observation, you subtract it off, square it, and you sum that up over all observations and divide by the population size, and that's called the variance. If you take the standard square root of that, then that's called the standard deviation. And what's useful about this is knowing the variability, okay, you can predict how often would you see a value that's 1 or 2 or 3 standard deviations away from the mean. So in other words, when we're doing our allele frequency sample, our research, how many people do we need to recruit if we want to capture rare alleles, right? Alleles that show up only 1 or 2% of the population. So we could enter, knowing the variability, we could enter that into what's called a z-score, and we could then find precisely how many are expected to be that allele and fewer representation. Okay, so little experimental design 101 there. What's the point about calculating variability? Is you could use that to predict the next research project. How many people do we need to observe to see these rare alleles? So a routine kind of thing to do when you've done an experiment is to calculate a measure of accuracy about your measure, and that's called the standard error of the mean. So you'd simply take the standard deviation divided by the square root of the sample size, right? So we'll call that SEM, right? And so it's kind of blocked here, but the SEM, the standard error of the mean, is always going to be less than standard deviation, and that's because, of course, you're dividing by the sample size. So the second little experimental design point is to point out that the larger your sample size, the more precision you're going to get out of your estimates, because obviously you're dividing the standard deviation by a larger and larger number. Okay, so I'm going to remind you here again. So all estimates come with error. The error is because of sampling. So we can quantify the error rates by using a thing called a confidence interval. And the confidence interval is approximately 2 times the standard error of the mean. Okay? So your book is fabulous, but that's one of the things that's missing in chapter 11 is the discussion of confidence and about the estimates themselves. All right, so this is an example of calculating the standard deviation and confidence intervals for binomial. Here are the equations. You can use an approximate method for the confidence interval. It's just, so here's our 2 again. This is more for a large sample, you're drawing from the normal population, so that's 1.96 to be more precise. Given that you're going to be doing some roundings, that's why I kind of make the argument that 2 is a good enough number. But then you just take the allele frequency of the one that you're interested, 1 minus that, then is everything else, divided by the sample size, and that gives you your confidence interval around your allele frequency. All right. Other measures of variability you're familiar with, we'll just do this really quickly, is the range. You take the largest, subtract off the smallest. Okay. Another one is the absolute mean deviate. So you just take the difference compared to the mean, take the the absolute value of that, sum them up all over that. So if everybody's close to the middle, then clearly the number will be small. As it gets larger and larger, that's a good indication that there's quite a bit of variability. All right. And then I always like to end discussion of the middle and the variability is by saying, look, if you want to make comparisons to different allele types or different observations, and there's a different scale, you can't just compare the standard deviations. You'd have to use, in fact, what's called the coefficient of variation, which is there's a relationship between the middle, so this is the mean on the horizontal axis, and the standard deviation. So the bigger as the mean increases, the standard deviation will also increase. So it's a biased measure if you want to compare variability among different characters that have different means themselves, right? So you just simply divide off the mean from the standard deviation, make it 100, so then it's a percent, and you can use that then to compare it. It removes the confounding of the size of the mean. So why would you do that?